All right, ladies and gentlemen, welcome to Unit 3 Ionic Bonding, Section 1, Ionic Bonding and Properties. So we already mentioned that we have atoms that will gain and lose electrons. When an atom gains an electron, it's an anion. When an atom loses an electron, it's a cation. And we kind of already mentioned that ionic bonding is really just this whole process, that when sodium on the left side loses its valence electron, it gives it to chlorine. That means it loses that energy level, it forms a positive ion because it lost that electron. Chlorine has gained an electron to have a full outer shell and is now a negatively charged ion. Okay? So let's get into the properties of bonding. So ionic bonds are bonds that form by transferring electrons from one atom to another. This changes their overall charges. That makes them ions. That's why it's ionic bonding. Positive cation, usually a metal, combines with a negative anion, which is a nonmetal. And so we're looking for, in ionic bonds, usually a metal with a nonmetal. I already talked about this, pretty much the same picture, but whatever. We transfer that electron over from one substance to another. The cation loses the electron to the anion. That means that they now are charged. So the cation is now positive, the anion is negative. That's where the attraction comes from for that compound to form. Okay, here's some properties of ionic compounds. So you might want to build a table or maybe just start to have a bulleted list of some of the properties so you can discuss those properties in your notes. So ionic compounds are all solid at room temperature. So every ionic compound at room temperature is going to be found as a solid, usually as a rigid crystal lattice structure. Okay, we already talked about that crystal lattice structure a little bit. We saw it in the web quest, but that's really caused by the attraction of the positive and negative ions. And so the positive has the attraction to all of the negatives that are around it. The negative is attracted to all of the positives, etc. So as mentioned, we start to develop the crystal structure. So when the circles are there, it's kind of, oh, nope, not that last one. When the circles are there, it's kind of hard to see the crystal structure, but as I start to draw in the attraction of the positives and negatives, you can start to see that rigid lattice structure. So that's what we're referring to when we're talking about that. So the positive ions and negative anions will kind of align themselves so that they're in a nice rigid structure like that. And that is a really strong attractive force between those particles. So that builds a nice structure of a lot of positive and negative forces holding it really closely together. So an interesting thing about ionic compounds is that they are able to conduct electricity. However, they are not able to conduct electricity unless they are dissolved in water. If you flip back to the previous slide, we showed that crystal lattice structure. When we have the positives and negatives that close together, when we have chlorine negative attached very closely to a sodium positive and another sodium positive and a chlorine negative, they've already transferred their electrons. And electricity flow requires the flow of electrons. So these substances, they've already transferred their electrons. They're not going to flow at all. So as a solid, there is no ability for the electrons to flow because they've already transferred. The electron is already on the chlorine. So it's not necessarily going to flow back to the sodium unless it is separated or unless it has to for some reason. Many ionic compounds are soluble in water, a polar molecule. I'll talk about solubility of ionic compounds in just a second. They have very high melting and boiling points. They have a really strong ionic bond, or ionic bonds are very strong. They have really strong formula units, so they hold together really strong, but they're brittle. And the reason they're brittle is this picture right here. So when we have a compound, we have all the positives and negatives lined up. So look at the first image. All the positives and negatives are alternating, so we have positive, negative, etc. But if I were to strike that and shift it, look right here. I now have two positives next to each other, two negatives, two positives. Those are going to repel. So these things are really strong, or they're very, they have strong forces between the particles, but if I shift the particles at all and I push the lattice structure down like that, if I were to attempt to hammer salt or anything else that's an ionic compound, it would crack because crystals crack, and that's really why crystals crack. So I'm going to be posting this video that's right here on the website. I want you to watch it. We are probably going to watch it in class again, but I would like for you to watch it either way. But this question is probably one of the most important questions that shows up in this unit, and you better believe that there's going to be a lot of questions on this on any assessment we have, as well as anything else we do in this class, because it is very, very important. Have I emphasized it enough? It's important. Let's add just one more star. All right, so ionic compounds dissolve in water. Why? Well, we know that it has to do with positive and negative charge. Well, one thing that's interesting about water is that this is what water molecules are actually like. The hydrogen end of the water molecule are slightly positive, and the negative end of the water, or excuse me, the oxygen end of the water molecule is slightly negative. All right, well, that's cool. We know that opposites attract to one another, so that means that the negative end of water is going to immediately be attracted to anything that's positive in the ionic compound, such as the cation. The positive end of the water molecule is going to be attracted to anything that is negatively charged, such as the anion. So when you put salt in water, it's not that it dissolves for any, magical reason. It's literally water saying, oh my gosh, this end of the water, the hydrogen end, oh my gosh, this thing is so attractive, let's grab it. And they grab the chlorine and they go off with it. The other end of the particle would say, oh my gosh, this positive thing, this is really attractive. They grab it, they go off with it. That's why salt dissolves in water. Not for any magical reason other than the fact that water is going to come in and is going to dry, and I know some of you were laughing because of the way I say water, Nick. Anyways, but the water is going to come in and drive this dissociation. Dissociation is another word for dissolving, because you are, if you are not associated with something, you dissociate with it, so you separate from it, which is what we need to do with a lot of the negativity in our lives. Just soapbox for a second. All right, so water comes in, pretty much drives this dissociation or the dissolving, and grabs onto the positive ends of the water, grab onto the anion, the negative ends of the water, grab onto the cations, and separate them. I do not know why the word water is right here in the middle of the sentence, but I am too far into this video to go back and fix this, so whatever. Electricity conducts because of free-flowing electrons. So free-flowing electrons are necessary for electricity to flow. And we already said that when it's in a solid, they're not going to flow because they've already transferred to where they're supposed to be. But if I separate them, then they're going to start to become desperate to rebond, to get back to their state of bonding or their stable state. So they're going to start transferring those electrons around. Okay? If electrons are not able to move, then a substance is considered an insulator. So ionic compounds are conductive when they're aqueous or when they're melted to liquids, because the ions are able to allow that the electrons to flow. And they're not conductive because I just said they don't flow. They've already transferred. So when they're in a solid state, that is just what they are. So this is another thing to reiterate. Water, even though it has positive and negative ends, it is not an ionic compound, so it doesn't have ions. So when water is by itself, it has no ions. Okay, and note this diagram even here says distilled water. What that means is that we've removed every single ion out of the water except for water itself. So it's only water in that container. When it's by itself like that, there's no ions. Water is a covalent compound, so it's not an ionic compound. So when it's like that, there's no ability for electrons to flow. In the middle, the solid salt, again, the positive and negative ions are already fixed together, so they're not going to conduct that current. Once they're separated, the positive and negative ions are able to move, and if there is a positive or negative current flowing through the liquid, then it allows for the electricity to flow, because I have positive and negative particles that can move in the right directions. All right, we're going to hit metallic bonds really quick, and this is really the most important image for metallic bonds. Just like with ionic compounds or ionic bonds, they are in a rigid structure, but I'm going to talk about why it's a little bit different. So when metal atoms come together, they have the ability to bond. And all metals form cations. So that means that the rigid structure of a metallic bond is all positive ions. It is all positive charges. Okay? Now there's still electrons around there, and the electrons are attempting to move from one electron or from one positive to the next, but they're being just all over the place. They're just being swirled around and not able to actually, really attach to one particular positive charge, so we call those delocalized electrons. So they're allowed to move freely. So that means they're already moving. That's why metals conduct electricity in the way they do, because they're already moving. The electrons are already able to move. In addition to conducting electricity, this also plays into why they conduct heat, but it allows the ability of that flow of energy in the form of electricity as well as other forms of energy. It allows for that flow to pass through a metal compound. All metallic bonds are solids at room temperature unless it's a metallic bond involving mercury, in which case it could be a liquid, but it usually isn't. They are malleable, meaning they can be hammered flat, and part of the reason that that happens and the reason that they're malleable and ductile and they don't break like ionic bonds or ionic compounds do is that if I were to hammer, look down here at this diagram, I have a bunch of positives. If I hammer it, cool, there's still positives next to each other, so it doesn't really matter. I don't know what is happening. I don't know what happened there. Anyways, so it doesn't matter if it's hammered or not. It's still going to be positives next to positives, which are not necessarily going to aggressively repel each other. They're already repelling each other to an extent, but because of their electron flow between them, they're holding pretty tight. So they're already in that situation. It's not going to be a unique situation for them. Okay, they have pretty variable melting, boiling point, hardness. Doesn't really matter. I'm not worried about that too much. But realize that the malleability and ductility does depend slightly on that sea of electrons by saying, oh, because all those electrons flow between them, it doesn't matter how it's hammered, those electrons are still going to pass between them. All right, hope you've taken some good notes. I'd like for you to make a quick reflection. I will be checking these notes, so please be ready to present them in class and make sure they are neat and organized. See you next class.